Hello, everybody. Welcome to the lecture 10 of Differential Privacy. This is a re-recording of the first half of the lecture 10 that I recorded yesterday. However, the Zoom recording had some issues that I didn't get to record everything on that was going on the board. So I'm doing this again. And the first half of this lecture will be pasted to the second half of the lecture. So you'll see a combination of these in a coherent lecture itself. All right, so for this reason, the annotations that you see over here is going to be slightly different from that that is shown on the course website for lecture 10. All right, I hope that's okay. All right, we'll start with a quick recap. So in the last lecture, we talked about we introduced this problem of differentially private machine learning. We understood the problem setup, the notations, and give a number of examples of why it is interesting and meaningful. Then we, from the statistical learning perspective, we define this problem and give a preliminary study of this problem to show what problems are learnable, what problems are not. And for the case of the finite hypothesis class, we've characterized its sample complexity of learning in both non-private setting and when we have when we require the data to be protected under differential privacy, right? And then we talked about the posterior sampling mechanism and gave some insight on how the posterior sampling mechanism or the exponential mechanism is related to the Bayesian philosophy. And in some sense, when the loss functions or the negative log likelihood functions are bounded, then we get differential privacy without actually changing the standard pipelines of sampling from a posterior in the Bayesian design of the model. Okay, so we left a new analysis of the posterior sampling mechanism, which doesn't require the loss function to be bounded to today's lecture, which is something that we'll start like in a little bit. So let's start from a quick recap. In differential private machine learning, so comparing to the standard learning, now we require the learning pipeline to be randomized. So now we have this differentially private learning algorithms that inject randomness in the learning process. So it effectively will sample from a probability distribution of classifiers or parameters of these classifiers, so that when we add or remove individual data points to the training data, and the output distribution of this classifier will not really change significantly. And this provides the privacy to individuals, and while still allowing these learned classifiers or hypotheses to capture the distribution of that the data is coming from on the population level. So a summary of the jargons that we used. So in machine learning, we typically assume that the data are, say, feature label pairs, and they are coming from some unknown distribution, IID, independently and identically distributed from some unknown distribution, and sometimes for concise notation, we call this data point Z1 to Zn, and this distribution is a joint distribution of feature label pair, and sometimes you don't have labels in those unsupervised learning problems, and then this Z is just going to be X itself. We also have a model. And this model is a family of classifiers, say the family of neural networks, where each element of this hypothesis class gives us a particular neural network with a fixed parameter configuration. And then each classifier, each H in the hypothesis class can take a data point and output some prediction on the label. So how do we measure the performance of a learning algorithm, and how do we measure the performance of a classifier? So we use something called the loss function to measure it. The loss function, denoted by this function L, takes one classifier and it also takes a particular input data point. And then it evaluates how consistent the prediction of the classifier on this data point is comparing to the given label. So one example of this is that indicator of h of x is not equal to y, which says that if your prediction is incorrect, then you suffer a loss of 1. Otherwise, you suffer a loss of 0. But it could be other things. It doesn't have to be this 0-1 loss. That is a canonical type of loss function used for classification problems. With the loss functions, we can also define the performance of a classifier through something called a risk. So the risk function is the expected value of the loss function of a fixed classifier when the data point is drawn from the same distribution. When a new data point is drawn from this particular distribution D, right? So this is what we call the risk, and this measures the expected performance, like the performance on average of this classifier for future data. Correspondingly, there's also this empirical risk that we define, which we put a hat on it. And this measures this is a function of the actually observed data, and this measures the performance of the classifier on the particular given data set. Therefore, it is an empirical estimate of the risk function. So we can see that this is the empirical averages rather than the actual expectation over the distribution. So the goal of a machine learning algorithm is to come up with H hat, a classifier that achieves as small a risk as possible. And because the risk doesn't necessarily go to 0, so in order to quantify how quickly we learn, we measure that by the gap of this classifier minus the best possible classifier within the class. And also this is equal to minus R H star. Yeah, we'll say that H star is the best classifier within the class, like for this distribution. The two typical settings that we consider in statistical learning are the realizable settings and the agnostic setting. So in the realizable setting, the underlying assumption is that there exists a classifier within the given family such that the risk is 0, meaning that you can predict all individuals' data points from any data point in the sample space that's supported on this distribution with perfectly with probability 1, and this is a strong assumption, and sometimes we don't wish to make that kind of assumption, right? So in this case, in the agnostic learning setting, we're simply hoping to match the performance of the optimal classifier, right? So this is an agnostic setting when our H star can be potentially like larger than 0 and arbitrarily like close to being trivial. So with that said, in the last lecture, we talked about how learning could happen and how to analyze learning algorithms and differentially private learning algorithms under the assumption that the hypothesis class is finite. Okay, the hypothesis class has cardinality that is finite. So using the Hofstein's inequality and union bound argument, we showed that the empirical risk minimizer, which basically finds the H that minimizes empirical risk, achieves an excess risk. So what is excess risk? So this is what we mean by excess risk. This is how much additional risks that you incur comparing to the best classifier in the hindsight. The best classifier that's representable within the class. So in this case, for the ERM, the excess risk scales like that in the big O notation. And we've seen that suppose we just run exponential mechanism and use the utility analysis, the standard utility analysis of the exponential mechanism that we learned in a previous lecture, then we can show that the additional error that's required by this differentially private algorithm is on this order. As we can see, it goes to 0 a lot faster comparing to like especially when epsilon is say a small constant, and this goes to 0 at a 1/n rate, whereas the non-private learning has this excess risk that goes to 0 at a 1/√n rate. So in this case, we can argue that at least for a large data set, then the additional cost that's required for differential privacy is not is going to zero faster than you are able to learn, even without privacy constraints. Yeah, which is a very satisfying observation. But some part of the issue is that the differential private algorithm is not able to easily adapt to the structure that's encoded in the problem. For instance, for realizable version of the problem, it is known that a non-private algorithm can achieve the so-called fast rate. So in this case, the empirical risk minimizer would achieve learning and minimize access risk with order 1 over n. On the other hand, the exponential mechanism is still just getting this 1 over n epsilon range rather than getting some additional benefit out of this assumption of being realizable. Okay, and then we talked about what if we want to generalize the assumption of finite hypothesis space into a continuous hypothesis space in a sense that now this hypothesis class H can possibly be infinite. Okay, and then we've seen a very pessimistic result, which says that no differentially private algorithm with epsilon parameter that's any finite value will be able to give us the consistent learning in the same sense of a non-private algorithm learning this hypothesis class. Yeah, so this is very bad, and the example actually has a VC dimension of 1, and from the non-private statistical learning theory, the VC dimension completely characterizes the sample complexity of a non-private algorithm learning this class, and a private algorithm simply says that even if the VC dimension is 1, and we cannot learn that with differential privacy. Yeah, so we'll see quickly how this argument works in the next slide. Yeah, and we commented that this is in some sense an artifact of the learning model itself for requiring distribution-free learning, in the sense that we require the learning algorithm to learn an arbitrary input distribution, even including those distributions that are somewhat contrived, and if we make additional assumptions on what kind of data distribution that we can see, or if we make assumptions about the Lipschitz property of the loss functions, and then these artifacts are no longer there, and we can actually learn with differential privacy. Yeah, so these points were not completely clear, but we will see some examples of that in the later part of today's lecture when we talk about the convex empirical risk minimization. Now, let's very quickly go over the packing lower bound, because it is a very interesting argument, and it makes use of the definition of differential privacy directly, which reviews the problem that applies to any differentially private algorithms on the information theoretic level. Okay, so the construction is the following. Suppose we since the requirement of the learning algorithm is the requirement of learnability is to for the algorithm to learn any distribution, and then we can construct a large bag of distributions and then show that if this algorithm is able to learn on all but one data distribution and produce some non-trivial results, then on the remaining one data distribution, the result will end up being trivial. Okay, so that's a general argument that we're going to be using, and we're going to be considering learning the threshold function parameterized by, say, a parameter h, and if and it will output output 1 if the input x is larger than h, and otherwise it will output 0, right? So this is a family of problems with VC dimension 1. Therefore, for non-private learning, it takes only a constant number of data points in order to learn that. And the hypothesis space, this is just a line segment between 0 and 1. So now let's try defining the k distributions on this disjoint support. So let's say that we partition, this 0 to 1 line segment into k disjoint regions, and on each regions at the center point of this, we can define h1, h2, all the way to hk, right? And we say that the distribution centers around each one of these hi, and on the left-hand side of this hi, this uniform distribution gives a label 0 or minus, and on the right-hand side of this hi, and each one of these distributions will give label positive, right? So this defines a family of k distributions, and the argument goes as follows. And suppose we assume that the differential epsilon differentially private algorithm A works on distribution 2, distribution 3, all the way to distribution k, and then we also assume that with sufficiently large number of data points, the expected error of this DP algorithm is smaller than 0.05, right? So this is a reasonable and somewhat weak criteria for an algorithm to be successful, because as n goes to infinity, the expected error is supposed to converge to 0. But let's say that it is smaller than 0.05 for a marginally interesting non-trivial learning result. Okay, so in order for let's say that this DP algorithm will output h hat to be anywhere. In order for this algorithm to achieve any non-trivial error, then the output classifier needs to be within the zone of the ballpark. It needs to be somewhere in the neighborhood of h2. If not, then this classifier will always classify at least half of the data points incorrectly, therefore resulting in an error rate of 0.5. Right. So what this is saying is that if the expected error is smaller than 0.05, then with probability at least 0.9, the output classifier of this algorithm A needs to be inside this region, needs to be within the correct ballpark. We're not even saying that it needs to be correct, it needs to output H2, but just it needs to be to be potentially correct, because otherwise, if you are outside this region, then with probability 0.1, then the error rate is already 0.005, which violates this expected error being smaller than 0.05 condition. Okay, so keep that in mind, which says that the probability of this algorithm under a data set of DI outputting something that is inside HI minus say eta over 3 and HI plus eta over 3 needs to be larger than 0.9, right? So this is H3, and this is H3 plus eta over 3, and this is H3 minus eta over 3. Okay, and the argument goes that we want to show, using the definition of differential privacy, that this algorithm doesn't work on the first distribution. Okay, so suppose D1 is a data set that you collect for the first distribution, then the probability of this algorithm on D1 being not inside this ballpark, H1 is larger than the sum is larger than the sum of the probability that I from 2 to k is larger than the probability of this being in say in H2, H3, H4, and that, because this is smaller than this region that's outside this support. Therefore, the probability of this algorithm outputting something like in the union of this disjoint region is a valid lower bound of the first probability. Okay, so this will become a D1 inside HI minus eta over 3 and HI plus eta over 3. Okay, and by the definition of differential privacy, and using the fact that the data set D1 differs with all the other DI when I is not equal to 1 by n data points, then by the definition of differential privacy, we can write that this is lower bounded by e to the power of epsilon times n. So this follows from the group privacy property. And then we can switch this d1 into d of I. So this is the probability of A bi being inside hi minus eta over 3 and hi plus eta over 3 in the interesting ballpark. And this is lower bounded by k minus 1 multiplied with e to the power of epsilon n, and like by what we know here, this is lower bounded by 0.9, and in this way, by choosing k to be e to the power of minus say 2 times e to the power of epsilon n, we can show that this is larger than 0.9. Right? So if the probability of being not inside the gap is larger than 0.9, and this implies that the expected error needs to be larger than 0.0 needs to be larger than 0.45 for distribution 1. Therefore, demonstrating that this DP algorithm cannot possibly learn on all distributions at the same time. Okay, so this is an interesting argument, and it can essentially be used to construct all sort of lower bounds for the pure differentially private algorithm that often is the optimal lower bound that one can hope to achieve. And then we talked about the exponential mechanism. So we said that so suppose we derive the learning algorithms through the Bayesian philosophy, then we sample from a posterior distribution, then this is effectively running exponential mechanism, and then we can come up with an asymptotic analysis by tapping into the large body of statistical literature and show that in this setting, when the loss function is bounded, then we can achieve like a little bit of blow up of the asymptotic efficiency, and otherwise this algorithm is the same, and it gives a high utility and consistent learning at the same time. Like even if we consider a continuous learning problem. So basically, whenever the posterior sampling works, then the exponential mechanism for differential privacy and also works, and it gives you consistent and almost sample efficient learning. On the other hand, like this bounded log likelihood assumption is sometimes a bit too restrictive, and the Minami et al. They've shown that one can actually analyze it using like more advanced mathematical tools, and assuming like something like a Gaussian prior, and that allows us to obtain stronger bound that allows us to obtain stronger bound that achieves stronger utility for the same ex posterior sampling algorithm without the bounded log likelihood assumption, and it also achieves interesting improvement in the privacy utility trade-off, right? So this is where we left off with in the last lecture. So in today's lecture, we're gonna first quickly go over the results of Minami and explain how their analysis works on a very high level. And then we're going to move on to talk about the convex version of differentially private empirical risk minimization, and talk about two common and intuitive algorithms to achieve interesting learning bounds in differentially private ERM problem. Okay, so here are some of the optional readings, and you should be able to get all the information you need from the lecture slides and the scripts themselves. But if you are interested in learning more and getting reading the original paper, like here are the references that you can look into. Yeah, for the opal perturbation and objective perturbation. All right, so we'll start with the improved analysis of exponential mechanism, aka the posterior sampling on the strongly log concave prior. So how is a strongly log concave assumption connected to the idea of strong convexity? So if this prior satisfies that it is it is equal to e to the power of minus some function r of theta, where r is the negative log likelihood of this is going to give us this r theta being the regularization term in your optimization problem. Then whenever this r theta is mu strongly convex, then the prior is defined to be so-called strongly log concave, which basically says that it concentrates around some locations and have a Gaussian-like doubly exponential tail. Okay, and I will define what do we mean by strong convexity more formally in a later slide today. So what Minami et al. Showed is that when the prior is chosen to be mu strongly log concave, and in addition, instead of assuming the individual negative log likelihood is bounded, all you have to assume is that the individual log likelihood is Lipschitz, right? So when you make this assumption, saying that the loss function changes slowly, and what do we mean by Lipschitz? Say there's this function. What the Lipschitz function means that it cannot change very quickly. So if you take any 2 points, theta 1 and theta 2, and the f theta 1 minus f theta 2 is smaller than some constant multiply the difference between the input parameters. It just basically says that like you cannot have like discontinuity. For instance, what is a function that doesn't satisfy Lipschitzness, like a step function? So suppose you have a step function like this, and you jump from one point to another without changing your parameter at all, then this function is not Lipschitz with any finite Lipschitz parameter L. Okay, so the algorithm is the same old algorithm. So we sample this parameter theta hat from the posterior distribution scaled by this parameter tau, which controls like how narrow and how wide this distribution is. And what Minami et al. Showed that this algorithm satisfies epsilon delta dp when R is mu strongly convex, that provided that we choose this tau parameter to be this quantity, then it satisfies epsilon delta dp. So how is this better than the pure dp result that we got through bounded loss function, right? So let's take a closer look at the objective function. So recall that this objective function is a summation of n items. So to this term, the sum of the individual loss functions is on the order of order of n. On the other hand, like this regularization is just on its own. So we can sometimes afford to take this mu parameter to be anything that's smaller than order n. Say that this parameter could be order square root of n. So when we do that, we can see that since L is a constant, and for any reasonable choice of epsilon, this tau parameter is actually going to infinity, which makes this distribution more concentrated than when we choose this tau to be 1, right? When we choose tau to be 1, this is a posterior distribution to be 1. And the distributions that you're sampling from using this posterior sampling mechanism that satisfy differential privacy is actually significantly more concentrated around the posterior mean. And this is a nice thing that says that if we have this property, that we can afford to get multiple samples from the actual posterior distribution without blowing up the privacy. On the other hand, we could also just get a more accurate estimate of the posterior posterior mean, so that we can end up getting like asymptotic efficiency of 1 as n goes to infinity, right? So everything is quite nice when the prior is nice and the Lipschitz and the loss function satisfy just the Lipschitz property. So how does it work? So I won't be able to cover the proof of this improved analysis of the exponential mechanism with too much details, but the general idea of the analysis is based on something that we have already learned. So the idea is to construct and analyze the privacy loss random variable of this method, and then apply the tail bound lemma that you've seen from the homework, so that if you can show that the privacy loss random variable has a being larger than epsilon is smaller, has a probability tail that's smaller than delta, then that implies epsilon delta dp for this mechanism. Okay, so maybe let's try at least working out this privacy loss random variable to see that this really makes sense to you. All right, so the definition of the privacy loss random variable in this context is a probability ratio of probability density ratio of output from the posterior distribution given D and the neighboring data set D prime. And when theta is drawn from, so P theta given D. Okay, so let's see what this looks like. So we know that this is sampling from a posterior distribution. So each one of these P is equal to e to the power of e to the power of sum I from 1 to n the log likelihood. That this is a little p and xi given theta, yeah, with the tau parameter, and plus the minus r of theta, and then divide by the normalization constant, which is the integral of this over theta. So this is normalization constant d theta. Okay, so similarly, in the neighboring data set, this will be the e to the power of I from 1 to n, the log likelihood, but plus this additional data point, log of p of x given theta, and now everything multiplied with tau minus r of theta. Okay, so everything is on the exponent, and then we're also dividing by this normalization constant of what is on the numerator and integrate over everything. Okay, so we'll call this normalization constant, I guess z prime, and call this normalization constant z, right? And then what this privacy loss random variable really is, because let's say that this log cancels with this exponential, and everything just becomes the differences of this log likelihood. And all we're left with, because this r got canceled out with r, and all the first n data point got canceled with the loss of the first n data point. So all we are left with is this minus log p of this additional data point that got added to the data set d prime, plus log of the prime minus log of d. Right, so notice that these two are constant. They have nothing to do with this parameter theta. And all we have to bound over here is to calculate this constant and calculate this privacy loss random variable on the theta drawn from p theta given d, drawn from the distribution induced by running our exponential mechanism algorithm on the data set d. Right, so provided that this is sufficiently bounded, this has a tail distribution that converges to 0 sufficiently quickly, and then we can also control the differences of the normalization constant, and then this gives us the tail bound of the privacy loss random variable. Okay, the exact technique of doing this is somewhat more complicated, which leverages the fact that both distributions on the numerator and denominator are strongly log concave, and because of it, and that together with the Lipschitz assumptions that says that the distribution of this theta satisfies something called the log Sobolev inequality, and by instantiating this log Sobolev inequality is using different like arbitrary constants, arbitrary functions. Then this technique simultaneously gives us a tail bound of the privacy loss random variable that is sub-Gaussian-like, and it also gives us a bound of the KL divergence. So recall that the expected value of the privacy loss random variable is really on the theta drawn from p theta given d. This is by definition the KL divergence of the two neighboring data set and of the distribution on the two neighboring data set. Okay, so using the log Sobolev inequalities, you can bound the KL divergence, and you can also control the tail of the privacy loss random variables in a similar fashion. And by putting everything together and working out the parameter regime, then you can get the results that I've shown I've shown in the previous slide. Right. So I won't be able to talk about the log Sobolev inequality because it's out of the scope of this course. But this is a very interesting and elegant technique. And if you're interested, please go to the original paper by Minami et al. And then learn about how to apply log Sobolev inequalities in this context. And maybe it will help your research in other contexts as well. Now, let's formally define the problem of a convex empirical risk minimization. So we'll go over what is a data set and what is a hypothesis class and what is our restriction of the loss function again. So the data is again, say x1, y1 to xn, yn drawn from some unknown distribution. The hypothesis class now is some prediction function parameterized by some parameter theta. So inside this, and this is equivalent to say that theta belongs to some convex hypothesis space. And in our case, we mostly take this convex hypothesis space to be R to the D. Okay, and the kind of loss functions that we consider for the convex empirical risk minimization are so H theta X Y. So we simply rewrite it to be L of theta X Y, right? And the requirement of the convexity is the convexity of the loss function with respect to its first argument. So L is convex in theta. A special family of this convex empirical risk minimization is a family of so-called generalized linear models. And in this case, the loss functions satisfy an additional particular form. So this L theta xy, this is equal to some f. So, and this f takes only the inner product of this theta transpose x and y. Okay, I'll give you a few examples of these generalized linear models. Say in linear regression, this is a standard square loss. And this is a square loss, and minimizing this, the sum of this square loss gives you the ordinary least square. And for logistic regression, let's say that this label space is -1 and 1, then we can write the logistic loss to be log 1 plus e to the power of minus y x transpose theta over 1 plus e to the minus y x transpose theta. Right. So why does this make sense? So let's try understanding this logistic loss from the two regimes. Let's say that this x transpose theta gives you a positive number and y is also a positive number. So in this case, your prediction will be somewhat accurate. And the more this x transpose theta is positive, and then you are getting something that's somewhat close to 0. Right, so this is the region, and if x transpose theta is x transpose theta times y is very positive, and then you get something that's close to 0. On the other hand, if x transpose theta y is very negative, this says that well, the second term dominates this log, and then taking the log of this effectively gives you. Effectively just give you a minus y x transpose theta, and this goes up linearly as x transpose theta gets larger. So the kind of loss function would look like that. Yeah. And it shoots up linearly. And then what this loss function does is that it interpolate between these two like somewhat smoothly, and that gives you logistic loss. And one can show that this is also like a surrogate loss function because it is an upper bound of the 0-1 loss, which gives you 1 if your prediction is wrong, and it gives you 0 if the prediction is correct. Okay, so this is equivalent to the cross entropy loss when the hypothesis space is 0, 1 cross entropy. But yeah, this is equivalent to the cross entropy loss in the binary classification problem. Yeah, just with the change of variable in the output space. In addition, there are other examples of the generalized linear model, say in support vector machine, and in this case, in the support vector machine, again, this y is from -1 to 1, and the loss function is a max of 0 or 1 minus theta transpose x multiplied with y. So it has a similar property, and the support vector machine's loss function looks like that. Again, the horizontal axis is theta transpose x, y, right? And this also gives another upper bound of the therapy loss function. So it's a hinge-like function. Therefore, it is called hinge loss. And we also know this by another name. That's like the hockey stick function that's flipped to the other side. Okay, I hope this convinces you that the generalized linear model is a rich enough family that is very commonly used. Okay, in order to actually talk about algorithms in convex empirical risk minimization and differentially private convex empirical risk minimization, I need to take a detour and tell you a little bit about the fundamentals of the convex optimization. So at least I need to define what a convex function means, like in order to proceed with our arguments. And this is also going to be very useful to you when dealing with these functions. And I'm going to cover some basic properties of these functions and inequalities that you'll end up using when deriving say convergence properties of these optimization algorithms, like in your other research projects. Okay, so what do we mean by a convex function? We say that f is convex if and only if for any x, y, and for any alpha parameter between 0 and 1, then f of x, f of the interpolation of x and y on the line segment that connects x and y, and it's smaller than the interpolation of the function value itself. Okay, so this graphically means that if the function is convex and we pick any 2 points, and then the interpolation is above the function evaluation f of interpolate. This is interpolate of f. Okay, there is a equivalent definition of the convex function for differentiable f. If f is differentiable, then the first order condition of a function being convex says that for any x and y, f of y is larger than f of x plus the gradient of f of x transpose y minus x. So what this is saying is that if a function is convex and we pick any points, then the local linearization of this function is always a lower bound of this original function. And this is linearization of f at x. This is x. Right. This is linearization. Okay, so sometimes the function being just convex is not enough, and we sometimes want to quantify the extent to which this function is convex and how convex this function is, which brings us to the family of strongly convex function. We say that f is lambda strongly convex if and only if, say a differentiable function, f is lambda strongly convex if and only if for any x and y, f of y is larger than f of x plus its linearization of fx. But then there's an additional term. There's an additional quadratic term, y minus x. This is saying that this function is strongly convex if you pick any points and it is supported by a quadratic function. Yeah, that's defined on the right hand side of this inequality, right? So this says that this function has sufficient curvature anywhere, and the change rate of the gradient is sufficiently large at any given point. Okay, so why do we care about convex functions? So in convex optimization, this is about finding the optimal solution, say that minimizes this function of x when x belongs to a convex set. So what this says is that in a unconstrained optimization, the optimal solution of this convex optimization problem is characterized by the gradient of this this function. So x star is a minimizer of this function if and only if the gradient of this function at f star is equal to 0. Okay, the right hand side is the local information, but it implies that this x star is a global optimal solution to this function, and this is what makes the family of convex function very nice, and it describes a family of optimization problems that we can solve with numerical solvers very efficiently. Okay, we need to define like a couple of additional properties of functions that are typically used in convex optimization. So we've already seen the Lipschitz constant of a function. We say that f is L Lipschitz if for any x and y, fx minus f of y is smaller than x minus y x minus y norm times L, and I guess this L is called the Lipschitz constant, and at the moment we're taking this norm to be just a Euclidean norm, right? You can define the Lipschitz constant with respect to other norms, but for now, like we will be using the most natural norm, the Euclidean norm. And in addition, the Lipschitz property of the gradient gives us some stronger, even stronger smoothness properties of a function. We say that f is beta smooth if for any x and y, f of y is upper bounded by f of x plus is upper bounded by a quadratic approximation of f at x. It's dominated by this quadratic function. So what to write it down clearly, we get half beta y minus x squared. So notice that this is analogous to that of the condition of the strong convexity, which gives a lower bound lambda strong convexity if f of y is larger than f of x, plus the same thing plus half lambda minus x squared, and this the strong convexity gives you a lower bound, and the strong smoothness, beta strong smoothness, gives you a quadratic upper bound, and these two together could give you that this function is sandwiched in between like two quadratic functions at any location x. Okay, so that's all we need to from convex optimization, and now let's apply what we've learned to design differentially private algorithm. And the first algorithm that makes sense for us to consider is whether we can just make use of the Laplace mechanism and Gaussian mechanism that we've learned from the previous lecture to solve this problem. How do we like we can obviously define this query of the data. We can define this query of the data to be, say, theta star, which is the arg mean of the empirical risk minimization. Okay, we can always define it this way, but then the question is that whether this function of the data is has a bounded global sensitivity. So by adding and removing any individual data point, how quickly does this theta star changes? yeah, the unfortunately the unfortunate matter is that the global sensitivity of this minimizer is not really bounded in general. So we can see that by looking at the by looking at the KKT condition, by looking at the optimality conditions through this gradient equals to 0 property. So what do we know about this theta is that the gradient of this individual loss functions at theta star is equal to 0, right? And on the alternative data set, what we know is that the gradient of say this theta star tilde is equal to arg mean of this alternative data set plus this additional loss function theta. Okay. Say this plus the gradient of L theta is equal to 0, right? So to these two together, like by combining these two together, it allows us to somehow calculate the difference between this theta tilde star and theta star. So let's do let's do a Taylor expansion over here. Let's do a Taylor expansion of that at theta star tilde. So we'll write by Taylor's theorem. By Taylor's theorem, this is equal to gradient of Li theta star, and plus some plus the second derivative of this sum of the second derivative of this Li at some v multiply with theta tilde star minus theta, and what is this v? This v is we know that by Taylor's theorem that there exists such a v on the line segment between theta tilde and theta star, such that the above inequality is true. Okay, with that, what can we see here? This is a matrix, and this is a vector, and on the left hand side, we have a gradient vector, right? So this is r to the d, this is r to the d by d, and this is r to the d, and this is some kind of a theta star minus theta star tilde equals to b thing, right? So it's described by a linear system of equation, but the issue is that like without additional assumptions, there really isn't any information for us to get that this A is invertible or this A is nearly singular, like bounded away from being singular. So it is possible to construct examples of within the convex empirical risk minimization problem such that this A has an eigenvalue of arbitrarily close to 0, and that makes it possible. So when we invert this A to the other side, the difference between theta star and theta star tilde can get arbitrarily large, right? So therefore the global sensitivity is not really bounded by any fixed constant. Okay, so the big idea here is to really regularize the objective function so that when we are working with a regularized objective function, then the global sensitivity can actually be bounded, right? So the idea is to instead of trying to solve the unregularized empirical risk minimization, now let's try to define this query of the data to be the arg mean of some of these individual loss function theta, but plus this additional regularization term lambda over 2 theta squared. Okay, so why does this help? So let's try let's try working it out. Yeah, so I guess on the other hand, so we can also define this as theta tilde star lambda equals to arg mean, and everything is the same, but then there's additional loss that's corresponding to this additional data point that we add to this data set or subtract away from this data set. Okay, so what is a global sensitivity in this case? So let's try applying the definition of strong convexity, because after we add this additional regularization terms, then this objective function that we're minimizing becomes lambda strongly convex, and we'll now apply this definition. Like for conciseness, let's define this part of the loss function to be L, the big L of theta. Okay, so what we know by strong convexity is that we can choose any x-y pair in the support of this function. So we'll have L theta tilde lambda being larger, yeah, I guess plus half lambda theta tilde square. This is larger than L, the actual minimizer here. And the term in the middle is going to be the gradient at this location multiplied with the differences of the parameter. But now the gradient is 0 because the optimal solution is theta star lambda, right? So we'll get we'll get 0 and plus half lambda. This is a strong convexity term, theta star lambda minus theta tilde star lambda square. Okay, so similarly on the other alternative objective that's coming from a neighboring data set, we can apply the definition of strong convexity again. Now plus this additional loss term, and this is larger than L theta star tilde lambda plus half theta star tilde lambda and plus L theta tilde star lambda and plus half lambda and theta star lambda minus theta tilde star lambda square. Okay, we're just applying the definition of strong convexity. And now what we basically do is to add up these two inequalities, and we can see that a lot of things got canceled out, and say this terms got canceled out with this terms, and this term got canceled out with this term, and all we got are just these individual loss functions corresponding to this new data point. And then what we can just consolidate everything and start from the right hand side. So we'll have lambda of theta lambda star minus theta tilde lambda star square is smaller than L theta star minus L of theta tilde lambda star. Okay, and we know that this L is Lipschitz, and so therefore we can first upper bound this with L by applying the definition of Lipschitz property minus theta tilde star lambda. Right now, by dividing both sides by their difference, then we can get the a bound on how much perturbation that we have being smaller than L over the strong convexity parameter lambda. Okay, this applies to all neighboring data sets. Therefore, this is a global sensitivity for the global sensitivity for this particular query F. And then we can actually now apply the Gaussian mechanism to this problem and then obtain differentially private algorithm. Okay, so again, the algorithm to solve the optimal perturbation is to first solve for the optimal solution by optimizing the regularized objective function plus some artificial regularization term that we inject. And after that, we basically add noise to this output parameter, release plus some IID Gaussian noise to every coordinate of this, and we choose this sigma parameter appropriately, so that we'll end up getting the epsilon delta dp that's calibrated to some predefined epsilon value. So if epsilon is smaller than 1, and then we can choose this by the classical Gaussian mechanism. We can choose this sigma to be proportional to the global sensitivity, that is L over lambda epsilon square root of 2 times log 1.25 over delta, and that gives you epsilon delta dp. All right. Okay, that's it's 2:16. Let's resume the lecture. I'll start slowly to talk about the utility analysis of this output perturbation mechanism. Okay, so there are two parts of this utility analysis, because we are doing actually, like, the first thing that we did was to modify the problem from a unregularized version of problem into a regularized version of the problem, right? So there are some differences that we get over there, so potentially lost in utility. And the second part of it is to add noise, so we can only approximate the optimal solution of the already regularized version of the problem, right? So this is and how do we measure the utility? So the most natural way of measuring the utility is to see how well we can minimize this loss function. So let's say that the loss function is given by this the loss function of this our output. So this is a differentially private output minus the loss function of theta star, where theta star is a minimizer of the loss function, right? So by saying that there are two parts of it, I'm saying that we can decompose this into analyzing, say, L theta hat P minus L theta star lambda plus L theta star lambda minus L theta star, right? And since theta star lambda and L hat P, they essentially they're minimizing two different things. They're not directly minimizing this L. So in order to analyze this, we have to work with the regularized objective function as well. Okay, so let's appeal to the let's maybe appeal to the smoothness of the loss function L in order to analyze this problem. Since we know that theta hat P is equal to theta plus noise, right? So this is our choice. So let's deal with the first term first by using the smoothness, and let's decompose this according to the definition of smoothness. So L theta star P is yeah, let's also add this as this lambda here, just for the convenience. So let's add this here and then Taylor expand around this function at its optimal solution. This is lambda theta star lambda plus half lambda theta star lambda square, and again the middle term is 0 because the gradient of this function is 0. So all that remains is just the theta hat P minus theta star lambda half beta. So we're assuming that the actually n times beta. We are assuming the individual L is beta smooth. Therefore, the sum over Li, I from 1 to n, is n beta smooth. Okay. So and then this is simply the noise. right? So this is a square L2 norm of the IID Gaussian noise. And when we move things to the other way, we can get L theta hat P minus L theta star lambda is smaller than half lambda theta star minus half lambda theta hat P square plus 2n beta, and then we can provide a high probability bound of this Gaussian vector, which looks like which is proportional to square root of d by simply the sub-Gaussian tail bound square root of d sigma times square root of d times 2 log d over delta. By simply bounding every individual components and then take union bound over the d coordinate, then this is the term that you can get. Okay, and this is negative, right? This is negative. This is smaller than 0, and we can drop that. So now let's deal with let's deal with this term. So how do we deal with this term? So so again, we can use smoothness. So L theta star lambda is smaller than L of theta star plus the gradient of L at theta star, and the gradient is 0. Theta star lambda minus theta star, like this is 0. So the middle term is 0 plus half n beta. So again, like this smoothness parameter of this function is n beta multiply with theta minus okay, and what we got over here is just it's just this term. So ultimately, what we want in the end is smaller than half lambda theta star square plus yeah, actually, like we can make use of another bound to try to bound this quantity so that we'll get something that's slightly different. So this is one bound that we can get. We can also use the fact that this L theta theta lambda is the optimal solution. So we can use this plus half lambda theta hat lambda. We know that this is always smaller than any other quantity. So this L star is another quantity, so we'll get half lambda theta star square, right? And by doing this, and we can bound the difference L theta star lambda minus L theta star to be smaller than half lambda theta star square minus half lambda theta star lambda square, right? If we apply this bound to if we apply this bound over here, and then we can see that we can see that so we'll write this term last. We will get half lambda theta star square minus half lambda theta star lambda square, and these two got canceled out, and then plus this additional factor of n beta sigma square root of d 2 log d over delta. Okay, so what is our choice of sigma from the previous page? So let's see, our choice of sigma is L over lambda epsilon multiplied with some logarithmic factors, right? So I realized that I shouldn't be using delta. I should be using, say, beta here, but I also can't use beta because beta is used for the smoothness. So let me use rho. Right, so this is a failure probability. So let's call it rho. But by substituting the choice of sigma, the noise level, into this expression. So let me erase this part, and then so that I have time to write it. I have space to write it. Let me erase this part. Okay, so 2n beta and this sigma parameter, it is so let's look at it again. L over epsilon and lambda and square root of 2 log 1.25 over delta, and also square root of 2 log d over rho, right? So let's not worry about these log factors. And now, like, we can see that lambda appears on the top in the first term, and lambda appears in the bottom of the second term, and we can minimize the bound by choosing this lambda appropriately, right? So by choosing lambda optimally, then we can get that this is the final expression that we get is square root of n beta L and I guess both log term to 1/2 in the square root and multiply with theta star and over epsilon, something like that. Okay, so this is not bad at all, because we know that the differences between these two is on the order of n. So if we divide this by a factor of n, we get the average error in terms of empirical risk that's going to 0 at a rate of order 1 over square root of n epsilon. Right. So this is the ultimate rate that we get from output perturbation. So it's yeah, I hope the analysis is clear, right? So the utility analysis is somewhat tricky, because we need to handle the part that's coming from additional regularization, and we also need to handle the part that's coming from the noise adding, right? So we're handling the noise adding by the smoothness, so that we can bound the differences by the magnitude of the noise, and then we can handle the differences that's coming from additional regularization through just this kind of inequality, which says that when we plug in theta star lambda, it is the optimal solution. Therefore it satisfies this inequality. All right. So the next mechanism that we'll talk about is a so-called objective perturbation mechanism. And the objective perturbation mechanism is more elegant and a lot more interesting compared to the output perturbation. It doesn't it's not a simple application of a Gaussian mechanism, but rather it requires us to actually work with optimality condition. So here's how objective perturbation works. So I'm talking about the epsilon delta version of the objective perturbation algorithm. So L is the sum of your loss function on this data set D, and R is some twice differentiable regularization. You can, like, for today, you can assume this R is just 0, and don't worry about it. And then this is an additional regularization term that we add as before, because it turns out we also need this for objective perturbation. And the idea is that now we are adding just a random noise term to the objective itself, rather than first solving the objective function and then add the result to the output. Yeah, that's the reason why it is called objective perturbation. And how this works is to simply sample this noise vector from a standard Gaussian distribution IID for every coordinate, take an inner product with your parameter, and then this create a modified, like, additional regularized and perturbed objective function. And then solving this objective function by plugging this into any off-the-shelf optimization toolkit will return something that's drawn from a distribution that's induced by the distribution of the noise that you use to perturb the objective. Okay, so this is equivalent to adding a random synthetic data point with a magnitude being B, and then the corresponding loss function for that random synthetic data point is a linear loss, right? So we're perturbing this objective by a linear loss of some like artificially created synthetic data point. And the claim is that this algorithm gives you epsilon delta dp when this lambda and sigma parameter is chosen appropriately. You could also hope to get the pure differential privacy by choosing this distribution of this b parameter slightly differently. So the Gaussian distribution gives you e to the power of minus b square over 2 sigma square. So this is a distribution of the Gaussian. And then suppose you just drop the square and then output some p of b being proportional to e to the power of minus b square over some parameter some parameter gamma. Yeah, without the square here. And then this distribution actually can give you the pure differential privacy. But like for today, let's deal with a simpler case that works with a Gaussian noise. So we've learned the optimality condition, right? Taking the gradient and set it to 0, and then we can work out the relationship between b and theta hat p. Okay, so let's do that. When we take the KKT condition, it's actually simpler, just a simple optimality condition. By taking the gradient and assigning it to 0, so we get the gradient of the loss function plus the gradient of this regularization plus we take the gradient of the quadratic function. We just get 2 cancels with this 1 over 2, and then we get this theta itself plus the gradient of the linear term, which gives us b, and this is equal to 0. Okay, and what we can do is to write this b, this noise b as a function of a theta, because whenever we get a b, then we can solve this nonlinear equation to get theta, let's write b as a function of theta as an inverse of this function. So b as a function of theta and also d is equal to minus the loss, everything minus lambda times theta. Okay, so this is our function that relates theta and b. On the alternative data set, when the data set is d prime, what we get is this, and I guess plus and minus this additional L, additional loss function corresponding to this additional data point that you get, but everything else would be the same, right? So this is only difference when we switch this function back to a slightly different data set. So what this function means is that suppose your data set is d and you are getting an output theta, and this is the noise that gives rise to this particular theta, right? So similarly, like when your input data set is d prime and your output is theta, and this is the noise value that actually gives you this particular output. Okay, so we know the distribution of b. We know that this b vector is drawn from normal sigma square I, but we're interested in the distribution of theta, right? And in particular, we're interested in analyzing to bounding the tail of the privacy loss random variable. Okay, so we are interested in bounding the log of p theta given d over p theta given d prime, right? But what we have is this b. So it requires us to use some tools called a change of variable formula and change of variable trick. So here's the general theorem of how we can do it. So let's say that x and y, they are generic random variables supported in R to the d, and let's say that there is a function that relates one random variable to another, and if we assume that this function g is a one-to-one mapping or bijective and differentiable, then the probability density function of one variable can be written as the probability density function of another variable multiply with determinant, the absolute value of the determinant of the Jacobian matrix of this transformation G. Right. So what is a Jacobian matrix? So this is like G takes a vector as an input and output a vector. You take every possible output, calculate the gradient with respect to that output, and then stack them up. Then that gives you the Jacobian. Right. So the Jacobian matrix in this case D by D, and this is a standard determinant of that Jacobian. And for those who are like still remembering your linear algebra, the determinant is a product of the it is a product of the eigenvalue of a matrix, and you can also like work out the determinant by a certain polynomial of all the entries, yeah, with a very complicated rule from that matrix. Okay, so let's now try applying this change of variable trick to somehow derive the distribution of theta, like using the distribution of B. So Y is our B. So B drawn from normal, and we're interested in the distribution of theta, and check that from the previous formula that this is our like this function is actually our G inverse function, because it takes theta and output B. So G inverse is the B theta given D. Okay, so G inverse takes theta and output B. Okay, and it requires us to take the derivative, to take the Jacobian of this B inverse, take the determinant, and then we can work out what this f of Y is. But yeah, to simplify it a little bit, so let's write it down in the notation that we're familiar with. So this is a probability of the density of our objective perturbation algorithm taking this data set, output theta hat P. This is equal to the normal density. This is equal to the normal density 1 over 2 pi sigma to the D, because it's D dimension, and minus the G inverse of theta. So this is, what is G inverse? G inverse is just B theta hat P given D square over 2 sigma square, right? So that's a normal density, and then multiply with the determinant of this gradient matrix of B. This gradient. So what is B again? B looks like this. So it says that we need to take one more derivative of this, and the first, the gradient becomes Hessian, and then this identity map becomes this identity matrix. So what we get is a determinant of minus negative Hessian of L theta given D plus minus the second derivative of the Hessian of R minus lambda times this identity matrix. So that's our determinant, and that clearly defines the probability density function of theta hat P. Right. So after applying this change of variable trick, we just apply the same formula to D prime again, and then it remains to take the log probability ratio. Okay, that gives us the privacy loss random variable. So let's do that. So what I'm basically doing is to now represent this Gaussian density with this new parameter, right? And then this determinant got multiplied to that. This determinant got multiplied to that in the alternative world. So this is log probability ratio. And then since the product of the log becomes a log of just the sum of the log of the product, the individual element of the product, then we can get these two. And then this decomposes the problem into bounding the part of the ratio due to the determinant and bounding the part of the ratio due to the probability density function of the normal distribution. The one is this star and the other is a double star. Right? You can convince yourself that this is right because log cancels with exponential, and over here we are just not doing anything.
Okay, so with that, and then we'll proceed to bound this star and the double star separately. So we'll deal with log determinant term first, and this requires us to use this lemma of rank 1 perturbation of the determinant. Okay, what this is saying is that for any matrix that is invertible, any invertible matrix A, and if we just add like a rank 1 matrix of CD transpose, and then we can calculate its determinant in this way by first taking the determinant of A and multiply by 1 plus this D transpose A inverse C. Okay, so this is a convenient formula that we can use over here, and the proof of this is effectively applying the matrix inversion lemma. But for now, let's take this lemma as is and then try applying it to solve our problem. Okay, so again, the hope is that we can maybe convert the denominator into something that's more similar to the numerator through iterative rank 1 update of this. Okay, so what we can do is to first decompose this. So the second term, yeah. So what we can do is to take the recall that when we take the Jacobian of this B function, like notice that this is B, this is the Jacobian of B, and when we replace D with D prime, the only thing that's in addition to what we already have here is this Hessian of this individual loss function, right? Either add or remove. So this individual loss function, let's take the eigen decomposition of this, and since this is convex, then we know that all the eigenvalues are positive. So we can take the eigen decomposition of this and it gives us U lambda U transpose. This is a diagonalization of this D by D matrix into this form. Okay, and this is a diagonal matrix of lambda 1 to actually mu1 to mu D. Okay, so actually I think in the equation like we use lambda. So let's say that lambda 1 to lambda D. And this is what we're doing. We're just doing the diagonalization of this like possibly rank D matrix into its eigen decomposition. So once we do that, we'll iteratively apply this lemma 25 by getting rid of each components one by one, right? So this is equal to determinant of B theta hat P D and plus say lambda 1 mu k plus and then minus plus sum over k from 2 to D lambda mu k transpose, right? And if we group these two together, and this one is a perturbation CD transpose, and then we can apply this formula to show that this is equal to determinant of plus D lambda. Now this is summing from 2 to D lambda k UK transpose multiply with 1 plus so this D and C, they are both this UK. So this is U1 transpose and A inverse, and this is A inverse U1 and that's it. And what we know about this A inverse is that this A actually have this lambda identity in it. So the smallest eigenvalue of this A matrix is actually larger than lambda. Therefore, we can bound this from above by we can bound this term from above by lambda 1 over this additional regularization that we add lambda. And together with this 1 plus, we'll have 1 plus this quantity. Now, notice that we can iteratively apply this. So ultimately, this becomes just the determinant of this B theta hat P on the D rather than on the D prime. And and multiply absolute value and then multiply with 1 plus lambda I over lambda, and then take the product from 1 to D. And by our assumption, this L is beta smooth, right? Which says that all the eigenvalues, which says that the largest eigenvalue of its Hessian is smaller than beta. So this can be further simplified into, from everything over here, and this can be further simplified into a bound of what we want under D, multiply with 1 plus beta over lambda to the power of D. Okay, so substitute into the previous term, and the determinant of under matrix D got canceled, and we are left with log of 1 plus beta over lambda to the power of D. And that gives me D times log of 1 plus beta over lambda. And this is roughly like when lambda is large and beta is small, this is roughly on the order of D beta over lambda. Okay, for generalized linear models, the bound can be strengthened a bit, because for generalized linear model, we know that the gradient we know that the gradient of the loss function looks like the following. So gradient of the loss function is in generalized linear model. By the chain rule, we know that this is equal to f prime theta transpose x y multiply with x, and this is a scalar, and this is a vector in R to the D, right? So to say it differently, when we further take the second derivative of this, then we get xx transpose multiply with a scalar. Therefore, like this matrix is only going to be rank 1, and we don't need to repeatedly apply this. So to say it differently, is for generalized linear model, we can obtain a stronger bound of the above that doesn't have this to the power of D on top. So ultimately, we only get log 1 plus beta over lambda for GLM. Yeah, for the second term over here, for the second term over here, and what we're going to do is to just use this inequality to use this identity of x squared minus y squared is equal to x plus y, x minus y, right? So this generalizes to the multiple dimension over here. And so it's a difference of these two multiplied with the sum of these two. And when we look at what is being look like, and you will see that the difference only gives us this differences in the gradient. Differences in the gradient of this individual additional individuals that we add, and the sum of this becomes like 2 times this b plus or minus this additional individual. And then this can be decomposed into the norm of theta hat p square plus an inner product of the this individual gradient transpose with 2 times this b vector. So observe that these two are not really independent to each other, but we do know that b is drawn from a normal distribution, right? So the output will affect what this look like. But however, for the generalized linear model, we actually admit a very like useful bond here, because for generalized linear model, we know that the second term is x multiplied with some scalar, right? And then the inner product with b, then x is fixed. Consider like x is fixed relative to this normal vector. Therefore, b transpose x is actually drawn from a normal distribution, a univariate normal distribution of this multiplied with a norm of x. Okay, so for generalized linear model, we can obtain a stronger bond, and the analysis goes by say, like we want to bound the second term with high probability using the fact that this is B is drawn from a normal distribution. And for generalized linear model, we can bound the second term through, like for the first term, we can bound it by L squared, by the Lipschitz constant, right? For the second term, for the second term, like we'll bond it differently for general problem and for the generalized linear model problem. For the generalized linear model, since we can work out that the B transpose X is drawn from a univariate Gaussian, and then we can bound the second term by sigma by sigma L and square root of 2 log 2 over delta, right? For the GLM, we can bound it with this, since this X norm multiplied with that scalar is always smaller than L. And that gives us something that looks very similar to the kind of tail bond that you get for the Gaussian mechanism. For the more general problem, the second term, the second term can only be bounded by the norm by Holder's inequality. And 2 times B theta hat D. Right, so this is a B noise, and B square is drawn from a chi-square distribution with degree of freedom being D. Okay, you can alternatively bound this with a norm of the normal vector by bounding every coordinate separately. So this becomes 2L multiplied with square root of D sigma square root of 2 log of D over delta. Right, so this is a bound that you get for the general problem. Right, so now we have everything. Now we have everything. If we just put everything together, which I don't have time to write down, but if we put everything together over here, so we have D beta over lambda, and over here we have L square over 2 sigma square plus say in the case of generalized linear model, we have some order of L. We have we have like dividing by sigma square, but we have a sigma on top of this, so we'll have 2 times log 1 over delta. And for the general problem over here, we have an additional factor of square root of D. Additional factor of square root of D on top. And what this is saying is that this algorithm, now that we have a tail bound of the privacy loss random variable, satisfies the whole thing being epsilon and this delta dp. Yeah, that's a full proof for the privacy analysis of the objective perturbation, which is quite cute as we use a change of variable and then bound the privacy loss random variables in an interesting way. Yeah, I'll like summarize the result and provide a more concise bound for the epsilon delta dp analysis of objective perturbation, and then tell you a bit about how we can do the utility analysis for this like more interesting algorithm in the next lecture. All right. Thank you all for coming, and I'll see you guys next Monday.